Okay, good morning students. Now coming here for the next session of analog IC design course. So let me recapitulate a little bit what we did last time. It was, we are discussing differential amplifier, and in this differential we are understanding the different mode of operation and the topology of this difference amplifier. What are the advantages if you tap your output single-handedly, and what are the advantages if you tap your output differentially. As I said, you can change the load from active to passive. Accordingly, the value will of the gain expression, wherever you have an RL, just replace RL by the active load value. Okay. I hope you all are revising your common source, common gate, common drain amplifiers, R in, R out, AV, frequency response, all those expressions, because that is very, very basic and fundamental. Unless you understand them, you cannot apply the concepts, and then you will find me as if I am rushing in the class. It will be difficult. This is something that we assume that you have done in your first degree, but I don't find that kind of a response from you, so I am revising a little bit. But I don't intend to spend too much of a time on this concept. So I request you again and again to revise the concepts again and again. So Razavi is the book you can go through. That gives you all single stage amplifiers. If you are not comfortable with Razavi, go for Cedra and Cedra. Okay. So we have discussed till now a differential pair. So its topology we have discussed, how to understand the topology of a differential pair. We have looked at the operation. Okay. Operation, within this we have looked at two operations, difference mode and the common mode operation. So we have the common mode operation. So I have discussed both of them and the advantages, plus we have looked at the characteristics also of a differential amplifier. Characteristics, which is very, very important for any IC designer to understand. Okay. So keep reading side by side as I cover the concept, so you go back and read it once again, at least once in a day you should read. Once this is complete, now I move on to the ADM and ACM. This is what I have found out. ADM, I showed you that you need not apply. The gain comes out to be GM times the load, RL parallel RO. And this is true even if you have the input applied differentially or input applied single-ended. This is true. And this is true only because there is a matching between the two arms. If the matching is not there, then this will not be true. Input will not split differentially equally, even if you are applying it to a single end only. Then it will not be true. So you have to ensure matching between the two arms. So load must be matched, the transistors must be matched. Okay, that is a condition. And when the input is single-ended, so you have to ensure matching, plus you also have to ensure the RSS to be very, very high. We request RSS to be very, very high. So we have to design current mirror accordingly. So once these conditions are ensured, I can apply my input single-endedly, and still I would be able to get a differential operation. Clear? Okay. Now we move on to something else. As I said that in ACM, you have to do ACM analysis. Okay. Whenever you have a input applied single-endedly. So again, you can draw the circuitry like this. It is ISS over here. this is input. So V in is common to both. So V in is V in. It is so same V in. So this is RL, this is RL, RL and RL are matched. So either you can go for the half circuit concept or you can go for the bending of or folding of the circuitry so that one simply coincides with the other. Do the analysis, find out ACM, So can you give me the ACM expression? I gave you an assignment. What is the ACM expression? ACM expression when input is applied single-handedly, it would be the same. It would be differential. If you tap differentially, the output will be 0. And if you are tapping single-handedly, what will be the output? What will be the output? It would be RL by 2 divided by, approximately, I am writing approximate expressions, RL by 2 by RSS, approximate. Drain resistance by total source resistance, so 1 by 2 GM. Because 1 GM here and 1 GM here. Net resistance looking into the source of the two MOSFET. The very shortcut method you can remember for a common source amplifier source degeneration. It is simple, a ratio of drain resistance to the net source resistance. The net resistance at the source actually RSS together with 1 by GM here and 1 by GM here, which is this. So 1 by 2 GM. Okay, and similarly RL by 2, they come in parallel, that comes out to be RL by 2. So this is the expression of ACM, very shortcut method. We have not taken any we have made approximations here. What are the approximation? RO is high and RL is smaller than RL. Under these approximations, and we are neglecting GMB, that is negligible. So under these approximations, we are getting approximate result. This will be ACM, and remember this is only when you are tapping single-ended output. Because if your output is differential, your net output will be 0. The net output will be 0. But if you tap it single-handedly, because there is no difference now taking, we are now taking any difference, in that case, you will have an ACM. So in the case of differential output tapping, so if you find out the CMRR, common mode rejection ratio, a metric for understanding the performance of a differential amplifier, just as you have a gain bandwidth product. Okay, here we have CMRR, common mode rejection ratio. So we want, what do we want? Because it has two modes of operation, we want difference mode to be high gain and common mode to be low gain. Because we do not want a common signal to replicate at the output, to get amplified at the output. That's why we get noise rejection capability. So we want ACM to be low and we want ADM to be high. So we define CMRR as mod of ADM by ACM, and this must be infinity. So here if you are having complete matching and everything you are getting, in that situation CMRR by default for a difference output tapping or differential output, it default goes to infinity because ACM goes to 0. If there is a mismatch, RLs is not matching, GMs are not matching, then you will have this value. It will not be infinity. Then it will not be infinity. Okay. Similarly, but for a CMRR, even if you have a matching, so when you are tapping single-ended output, then there would be a CMRR. Because then there is no output not going to 0. So here we get whatever ADM you have, GM, RL parallel RO, divide by this RL by 2, approximate relationship, upon RSS plus 1 by 2 GM. This would be your CMRR. So nobody says that you have to tap the output single-handedly. That's your wish. You may go for differential output tapping, or you may go for single-handed output. It's your convenience. It's your requirement. Designer says, okay, I want differential amplifier in this fashion. I want to use it in this way. It's okay. Nobody is going to question you. Okay. So how to use a particular structure, that is totally a designer's discretion. Clear? Now we move on to the next, that is the load. So now I come to active, current differential amplifier with active load. Now it is a special term. You can say I can replace RL by a diode connected MOSFET. It is an active load. I agree. No issue here. Similarly, I can replace with a diode connected PMOS, NMOS, current mirror. Okay, I agree. These are all active loads. But a special term for which this active load current differential amplifier is reserved, it is for a given specific topology. Okay, what is that? I have an amplifier, differential pair. This is ISS, grounded. So V in 1 and V in 2. V out, V out. This is RL, this is RL. This is my differential amplifier. Now let us see what happens if you tap your output single-ended. The gain becomes half. But tapping the output differentially means you get the output from two nodes, one positive and one negative. So if I have a next stage to it, that should also have two input. That means a differential amplifier has to be followed by another differential amplifier. Then you cannot cascade a common source with differential pair, because common source amplifier has only one input, whereas output coming from differential pair is two nodes. So either I should have a differential pair, a cascade of differential amplifiers, or I have to tap my output single-endedly if I am cascading differential pair with CSA. So if you are tapping it with a CSA, in that situation I can tap only one node, either this one or this one, any one. You have to take only one of the input. The moment you take one of the input, your gain becomes half. So I am losing on the gain and the flexibility of cascading. So either you get a gain or you have the flexibility in cascading. Okay, either you have a only cascade of differential pairs, then you will get the gain benefit, or you can have a flexibility in cascading, cascade differential pair with any of the single stage amplifier, but then you will lose on the gain. Low frequency gain, or this is also called as a DC gain. It's not related to DC voltage, remember that. Low frequency gain is also called as AC gain at low frequency, means I call it as a DC gain. So what to do? So can I get something? I will be able to get the flexibility in cascading. At the same time, let me have something or do something such that I do not get a loss of gain. So here is something which we now call that differential pair with active load. So what is that? So very simply what is done. If I am tapping this output, suppose I am not tapping this output. So here you will get the gain approximately half GM RL or RD. Okay, this will give you another half, so half and half they get added up and you will get a complete GMR. So if I am not tapping this node, if I am only taking my output from this node, then can I somehow reflect the impact of this node onto that node, onto my output node? If this is my VL, can I reflect the effect of this node onto the next node? Because effect at this point is coming from V in 1. If you are not reflecting, then you are simply discarding the impact of V in 1. So as if only your differential pair has only half the input. Though you are applying the full input, but it's working with only half the input. So can I reflect the impact of this node, V out, this V out onto the next node? So we should have a reflection mechanism, a kind of a reflection mechanism. So what is to be done now? So you have now a circuitry. This is ISS. This is ground. This is V in, say minus. This is V in plus. and my output is being tapped from here, and here you have a CSC. Maybe an active load. This is V out. A CSC. Okay. If you are tapping this node, so I should have an impact here. So if this is plus V in, this will have a current GM times V in. So if I say V in plus minus V in is equal to V in, so this will be GM V in by 2. Let me call this current as I. So here the current through this will be opposite current but of same value I. It would be exactly the same value but an opposite polarity, because there you have a minus V in by. Fine. So what is to be done? So this will, if I have an R out here, so net potential at this node AC would be simply, if I say this is my V out, so V out is going to be minus or plus, if it is minus, GM V in by 2 into R out. Or simply V out by V in by 2 is equal to GM R out. Or simply, sorry. Okay. This will be my output. Positive polarity because input is negative here. Because input is minus. So what is to be done? So I have to reflect the mechanism. So this output will now, what will be this output? Let me call this is my intermediate node Vx. Potential here is going to be minus GM V in by 2 into R or R out. Whatever is the resistance at this node. Whatever is the resistance at this node. So AC current dropping across the net R out. AC current is generated by the amplifier, the differential pair. So what is to be done? Reflection mechanism. Changing of, reflecting one input or replicating, mirroring one current into the next term. That's what I have to do. So I can have this I current. If I can bring this current high here, this I reflected here. So then the net current through this will be 2I. Net current through this will be 2I. So in that case, my net output, V out by V in will become now, this was what? I. This will become 2I. So that will give you twice of GM R out by 2. I am getting the full gain. I am getting the full gain. So I need to mirror. So the moment you have a mirror means there has to be a current mirror. So what I do, I put a current mirror. Now this current mirror has to be PMOS because it is connected to the source. I put a current mirror here. A PMOS current mirror load. It is not a setting the bias current. No. It is not setting the bias current. It is only acting as a load here. Current mirror load. Now we call this as a differential pair with active load. So what is happening is that a current I through this, because they are in series, this also has to carry a current I. This also has to carry a current I because they are mirrored. Okay, so if this is M3 and M4, both PMOSes, they should be matched. So this must also carry a current I. So this I and this I, together they will come out of this node KCL, will cause a drop across R out. It will cause a drop across. This is giving you a single-ended operation without loss of gain. This gives you a single-ended operation without, so I can tap my output not single-endedly and still there would be no loss of gain. But what I have lost is symmetry. Now can you see the load is unsymmetric here and here. Here the net load is 1 upon GM. Whereas here the net load up is RO. So symmetry has been lost. Now you do not have a matched arms. You do not have matched arms. I can have matching between transistor, but differential amplifier topology is no longer matched. So again there is a problem. You may have differential operation not happening because symmetry is required for difference operation. So if you have a unmatched or unsymmetrical differential load, what are the conditions in which you will get difference operation? You can still get a differential gain. Naturally, the moment there is a unsymmetrical load, this node will never come to AC ground. So now there are two reasons why this node will not be at AC ground. One is because you are applying your input single-handedly. Second is because the load is unsymmetrical. They both will cause an AC voltage to appear at this node. Now suppose I work with the same concept. Let me apply my input single-handedly, differentially. So that the first cause I am removing. First source of AC voltage I am removing. So let me apply V in plus and V in minus so that this will give me AC ground here. This is not causing any AC voltage to appear over here. But unsymmetry will cause an AC voltage appear here. So let me see under what conditions now I will still get a difference operation. So I'm not including, or I'm not saying that my input is single-handed. I'm saying my input is differential. So that I'm removing one cause of AC voltage. Now I have a second cause only existing, that is unsymmetry of the load. So now we have to see whether what should be my ISS, what shall condition on my other parameters so that I still get a difference operation. Okay. So let us go for the difference mode operation. So we have something called ADM. Now I need to look at A difference mode. Again at low frequency. A difference mode. Okay. So A difference mode is very simple. Now I can now draw an AC model right here. So this would be replaced by 1 by GM. So I am redrawing. This is 1 by GM3. This is M3, say this is M1 and this is M2. I am using subscript now. M1 and M2 are matched. M3 and M4 are matched. So I have GM3. This is VDD. This is MOS. Okay. This is M4. So this connects here. And I have a MOS here to which I am feeding V in plus and here to which I am feeding V in minus. And this is ISS whose resistance may be RSS. This is equivalent to a current source with a RO. M4. This is equivalent to a current source with RO. So current source, this is source and this is drain. Current flows from source to drain. Okay. Now what is the potential here? Potential here will be, if I say Vx, what is going to be my Vx? This current, which is Gm times V in by 2. Okay. So this is I is equal to Gm V in by 2. So drop here will be minus Gm times V in by 2 into 1 by Gm3. You may say this has to be RO coming from here. Okay. RO. Then why RO? Find out the net R out here. What will be net R out here? Let me say R out 1. It would be 1 by GM3. Parallel. Now parallel structure will include all this. Parallel from here will include this also and this impedance coming from this branch also. So if I draw downwards only, it would be RO1. This would be RSS. And impedance coming from here. What is the impedance coming from here? It is a common gate configuration. R in of a common gate. R in of a common gate. I told you last time it is. R in of a common gate is load plus RO 1 plus GM RO. Load here is, what is load? Load of M4. So it is RO, RO4 plus RO2. Assume all ROs are equal, so it would be roughly 2 RO by roughly GM RO, which is nearly equal to 2 by GM. So I know now that this impedance is going to be now 2 by GM. I am looking here. This is my R out point. So what is my R out now? Compute. It would be 1 by GM3 parallel this whole component. So can I say it would be RO1? Rather, remember you have a MOS here. Okay? So cascading will come. I can remove this from here and put it in parallel to this. It's like a cascade. A MOS with source degeneration. A MOS with source degeneration, I can apply the concept of source degeneration to this MOSFET. So this will give me, what is this component I am writing? GM1, RO1, or what is the parallel of this? 2 by GM. 2 by GM parallel RS. Okay. So it would be 2 by GM parallel RS. Plus, it should be 2 by GM parallel RSS plus RO1. Now put this over here and get me R out. Make suitable approximations. What will be R out? What will be R out? This is going to be 2 by GM. This is RO1. And this will be 2 by GM. GM, suppose GMs are equal. Suppose GMs are equal, GM is cancelled out. What do you get from here? RO plus 2 by GM plus RO, roughly 2 RO. You will get it as roughly 2 RO. The moment you have roughly 2 RO, so now I have this R out coming as 1 by GM3 parallel 2 RO. It is 1 by GM3 parallel to RO, which is nearly equal to GM1 V in by 2 into 1 by GM3. Assume all GMs are equal. This is roughly equal to minus V in by 2, if I am not wrong. So minus V in by 2. Actually, at this potential, the AC potential comes out to be minus V in by 2. Approximately, I am assuming GMs are equal. Otherwise, GMs may not be equal. Okay. So once you have got the potential here, so this will have a gate voltage, AC gate voltage. So it will produce a current GM times VSG. It's a PMOS. GM times VSG. Okay. So what will be the I? How much I will be generated? It would be GM4. Okay. So GM4, so what will be this? GM4 remains as it is. Now which direction? If I draw its model, this is RO4. Which way I should put the current, this way or that way? The current flows from, if a voltage is applied at the gate, now depends which polarity, positive or negative. How should you draw the current type? The same concept, when VGS increases, current increases. So when VSG increases, the current increases. Through PMOS, current increases means I source to gate, I source to drain. So when you have a positive potential at a PMOS, a positive here means VSG is reducing. Means VSG is reducing. My normal flow of current is I source to drain. So current should be this way when it is increasing, should be other way when it is decreasing. Now you are having a negative potential here. It's a negative value. So ISG is or VSG is increasing. So current should increase. So current should flow from source to drain. So it should be my direction. This must be my direction. So I have a current GM4 VSG. Okay. So I can write it as GM4. Now I will not put a minus sign here. Remember, because I have taken care of polarity by choosing proper direction of current. So this would be GM4. What is VSG? I know VSG is V in by this potential here. And this potential is given by this. Vx. Vx. So this is nothing but GM4 Vx. This current will be GM4 Vx. So I have now GM4 Vx current component as equal to I as equal to GM4 into Vx is how much? GM1 V in by 2 into 1 by GM3. And this cancels out. Because both are matched. Because both are matched. So this gives you a current of GM1 times V in by 2. So this current component is GM1 times V in by 2. Clear? Everybody has understood? What should I repeat? How do you get this? What is this? Tell me. It is a current through M4. This we have got. I am not putting any sign because I have taken care of the direction. So what is GM4 Vx? Vx is given by this expression. Substitute Vx here. Do not put minus sign because it has been taken care of. I have got the value as GM1 V in by 2. So now I have this I and this I. Can you see two I's? Okay, this current I up is GM1 V in by 2. This current is also GM1 V in by 2 with opposite direction. So KCL says that it has to come out of this node and drop across the R out. So what is R out at this node now? Tell me. What is R out at this node? R out is RO4 of M4 in parallel with the net impedance down. What is the net impedance down? Now tell me. You have done it so many times. Compute. Compute this. Let me say this is R1 component. So R1 parallel RO4 will be your net R out. Let me not say this is RL because this will be confusing. This is RL. Okay. So what is what is R1? Compute what is R1. R1 is looking down this way. So you have an RSS over here. And the impedance coming from this branch. Net impedance coming from this branch. So start from here. MOS. This is getting you a MOS. So what is R1? So you have a MOS. This is R1. You have a MOS. Then down is RSS. So you have RSS and then this entire branch. This one is, what is this? 1 by GM3. This is again a common gate with load as 1 by GM3. Again use the same relationship that we find. Common gate input impedance. Common gate input impedance. I don't think you people are you getting me? Huh? Yes or no? Goa campus. Are you people getting me?
Yes, ma'am.
Okay. So now what is this? This is going to be common gate with 1 by GM3 load. Look here, common gate, it is common gate. This MOS input here, sorry, this is now, when you find R out, this is grounded, remember? When you find R out, input is grounded. So this node grounded, the load is 1 by GM3 and you are looking from this point, so this is the input point for you. So this is common gate with 1 by GM3 load configuration for you. I can directly apply the Rin concept of common gate. So Rin now comes out to be, can I write a single amplifier, a single resistance. I can immediately find out the result. This is RL. RL will be 1 by GM3. 1 by GM3. So 1 by GM3 plus RO divided by 1 plus GM2 RO or GM1 RO. Solve it. What do you get? Solve it. What do you get? RO you can retain because 1 by GM3 will be small. So RO divided by GM RO. It would be 1 by GM1. So this is going to be 1 by GM1. So what is R1 now? Tell me. R1 will be GM2 RO2. What is a parallel combination? 1 by GM1. It will into 1 by GM1 plus 1 by GM1 plus RO1, RO2. This is coming as 2 RO roughly. Approximately. This will come as 2 RO. So this 2 RO is going to be your R1. So R out is coming out to be 2 RO parallel RO. So this impedance is RO4 parallel 2 RO. So what is your net gain? What will be net gain? It is net current 2I dropping across RO4 parallel 2 RO. This gives you 2I is 2 into GM V in by 2 into RO4 parallel to RO2. Okay, so this cancels out. You get a gain of GM V in approximately, can I say, RO or whatever value you get to RO2, which is roughly similar to, I will put a negative sign or a positive sign, depends what way current is flowing. If the current is flowing out, it would be a positive polarity. If current is direction is opposite, it would be a negative polarity. Here it would be a positive polarity. Net gain would be given by this, which is similar to common source amplifier. Similar to common source amplifier. Got it? So this behavior, you are still getting a current of or operation and difference mode. You are still getting a current gain or voltage gain similar to common source amplifier. But here remember we are using RSS to be much greater, so RSS must be high. RSS must be high. Okay, you should have RSS to be high. And here I cannot take this node to be AC ground because it is not. Even if you are applying your input differential, it will not come to AC ground because of unsymmetrical load structure. But still, you would be able to get a difference mode operation. Just make your RSS large so that you can make this approximation and then everything will go well. So I cannot use a diode connected MOSFET as my ISS. Can I use? No. Because the moment you use a diode connected MOSFET to supply ISS, RSS will become 1 by G. Accordingly, things will change. So try to make RSS large. So whether you apply your input single-handedly or you tap your output single-handedly, both the situations try to make RSS large. We should try to make RSS large. Got it? Single-handed operation. So can you do common mode operation? Same analysis, current mirror active load. Okay, but now doing ACM and finding out CMRR. Again, remember you have a current mirror load structure of a differential pair. This is ISS grounded, V in minus, V in plus, VDD. This is V out. And this node is Vx. Say M3, M4, M1, M2. And you have an impedance RSS. So can you find out the ACM? ACM is this node. Naturally now here, since there is no difference mode, no differential output tapping, ACM will exist. ACM can never go to 0. You can minimize it, but you cannot not make it 0. In differential output, you will automatically get it 0. The movement matching is retained. But here we cannot get. Here we can't get. I think in Pilani campus some student is absent. I feel low strength today. Is somebody absent today? Is somebody absent? I'm saying yes or no. Who is absent? Only one person. The way I give you a task, every day you will take the attendance of this class. Whenever I have a class, you will be taking attendance and maintaining the record. Make a file. Okay? Fine. Clear? Is this clear to all of you? Now you can do the analysis right here on the circuitry itself, just as I have done for the difference mode operation. Okay? How to split? Very easy. You can make it as 1 upon GM3. I am drawing the model, but you can analysis you have to do. I will not do the analysis. This is Vx. This goes to a MOS. Remember, MOS is going to be a model. It is GM Vx. This would be AC ground. This is RO4. This would be Vx. Okay? So current direction I have shown, so that it make it, I have shown, taken it downwards. So this will automatically be modulus, because appropriate current direction has been chosen. Now, each arm I can split now. So this would be a MOS. Okay, so a MOS. V in is going to be common to both. A MOS here, and then RSS, it would be RSS by 2. One way, or let it be RSS. Let it be RSS. This would come here. Another MOS, M2. This node is again V in. It is the same V in. It is the same V in. So it is a V in only. And this is coming here. This is your V out. ACM you have to find out. ACM. So that means you have to find out V out by V in. V out by V in. So if you are applying your V in here, find out this potential. If you apply your V in here, find out this potential and use superposition theorem. Use superposition. So first of all, what I will do, I will apply V in here and make this grounded. Find the value V out by V in. Okay. In second case, I will ground this. Apply V in here and find out the value V out by V in, and then we use principle of superposition. Okay. We use principle of superposition. In both the cases, find out V out by V in and simply add with proper polarity. So you will get the net result V out by V in, which will be your ACM. Can you do it? May I leave it to you? You all know principle of superposition. So do it one by one. Do it one by one. Go on applying the concepts. Go on applying the concepts. Clear? I hope you all can do it. So find out ACM, and once ACM you have found out, this would be find out CMRR. We have got ADM, you have got ACM, find out the difference. And try to find out the condition under which CMRR tends to infinity. CMRR tends to infinity. What condition you require for CMRR to tend to infinity? Can you do this? Please take it as a take-home assignment and do it. Do it. I am saying do it means you have to do it. You may consult each other, sit together in a group, do brainstorming and do it. Do it. ACM I am leaving analysis to you. Okay. So we have got current mirror acting as active load. With active load, the analysis has been done. You know the two topologies, fully differential, where you give your input differentially, output single-handedly, differentially, a fully differential topology, and a current mirror load topology, where you give your output single-handedly, yet you will get a differentially. You will get a differential input, but your output will be single-handed output. We have understood both the operations, and now you come to mismatches. Mismatch. What happens if there is a mismatch? So how to do the mismatch analysis? So all analysis I have done, but I will not be uploading it because I want you to do the ACM on your own first of all. Analysis is there which you have to understand and do it. This is for your reference. Derivations, you have to understand the derivations and do it on their own. Do not take what I have written in the slide is correct. Do not assume. There may be a mistake. So check the validity first on your own and discuss with me. Clear? But I have tried to do derivations wherever I think it is necessary. Clear? Now this is the noise behavior. Look here, I am giving a small noise signal here. The noise signal is going to be common to both. To V in 1 as well as to V in 2. Noise signal will be common. So noise signal impedance, the net potential here will be minus delta Vn noise. You can compute the AC values now, assuming that it is an AC analysis with signal as a noise signal. Find out the noise signal, get the net ratio, and find out the net noise voltage appearing. Net noise voltage appearing. And you will not find much. You will not find much. Why? Because it is now, instead of V in by 2, assume a delta Vn noise. Do the entire analysis. Do the entire analysis. So one signal coming from here, another signal coming from here. And net difference will be addition of the two. Principle of superposition you have to do. Principle of superposition you have to use. Okay? Noise behavior. So in a current mirror load, what have we lost and what we have gained? Symmetry of arms is lost. I have done this analysis. Okay? Gain, ADM I have done. Okay? And then come to ACM. Do it yourself. I shall not be uploading it. You will be doing it on your own. Okay. So RSS, as I said, RSS will play a crucial role. RSS now has to be large. I cannot use a diode connected RSS now. I could have used an RSS as 1 by diode connected load, in which case, when your this node P node comes to AC ground, then I can use. But the moment you apply your input single-handedly or you tap your output single-handedly, then you cannot use RSS as a diode connected MOSFET. No. Then it is a strict no. RSS has to be large. Okay. So examples are there which I request you all to have a look out. Now there is a mismatch. If there is a mismatch, okay. So that is what I am showing you. What will happen to P node when RSS is small? You will not get a difference mode operation. VP will not give you a correct operation. I request you to go through, and then RSS has to be large. This we will do little later. How to realize high RSS current mirrors. You all know Wilson and Cascode. These are those current mirrors. Design tips, small signal analysis, the capital GM calculations for a differential pair with active load, okay, and R out computations for differential pair with active load. As I said, you should know capital GM and R out values of every topology. Clear? So now we stop here. Bell has gone. So next time I will revisit this differential pair a little bit, because some concept is still remaining, and then we will move on to the frequency response of amplifiers. So please revise your concepts of body plots, phase margin, gain margin, pole frequency, zero frequency, transmission zeros. Kindly revise. Unity gain bandwidth, minus 3 dB bandwidth. Kindly revise those concepts. Any query from Goa campus? Any query you have? No. Okay. So we stop here. Thank you, and we'll be meeting next class. Okay, I think ME students, we have a demo for our first degree students, cadence demo, for which I require your help. So you will be called by Nitin sir and you have to help us. Demo is on Friday. Okay, I hope he must have called few of you. So you should help us with all your support.